Well, in the previous lecture, we began to discuss C-star algebras, and we approached the first fundamental result, namely the first Gelfand-Naimark theorem, or the commutative Gelfand-Naimark theorem. Unfortunately, we had no time to formulate and to prove this result at the previous lecture, so this will be our first goal for today. The first Gelfand-Naimark theorem. So to begin with, let's recall two fundamental results about C-star algebras, which were proved at the end of the previous lecture. The first theorem is about the spectral radius. So suppose that A is a C-star algebra, and little a is a normal element of A. So let's recall that normal means that A commutes with A star. Then the spectral radius of A is equal to the norm of A. So let's recall that in the general case, that is for arbitrary Banach algebras, the spectral radius is less than or equal to the norm. But the point is that for normal elements of a C-star algebra, we have an exact equality. And theorem 2, which was proved at the variant of the previous lecture, is about the spectrum of self-adjoint elements. So suppose that A is a C-star algebra, and little a is a self-adjoint element of A, which means that A star equals A. Then we proved that the spectrum of A, or more exactly the non-unital spectrum, because we don't assume that A is unital, is real. The spectrum of a self-adjoint element is real. And of course, in the unital case, this is equivalent to say that the spectrum itself is real, because for a unital C-star algebra, the only difference between the spectrum and the non-unital spectrum is 0. So 0 is always in the non-unital spectrum. But of course, 0 is a real number. So if A is unital, we can just replace the non-unital spectrum by the spectrum here. Okay. Let's introduce, it will be convenient to introduce a special notation for the set of all self-adjoint elements. So the set of all self-adjoint elements will be denoted by ASA. That is the set of all self-adjoint elements in A. And it's clear that this set is a real vector subspace of A. It's a real vector subspace. Of course, it is not a complex vector subspace. When we multiply a self-adjoint element by a complex number, the result will be self-adjoint only if we multiply by a real number. So it's a real vector subspace. Clearly, it is closed in A. Let's now deduce some corollaries from the previous result. Corollary 1 tells us something about characters of a C-star algebra. So if A is a C-star algebra, and chi is a character of A, that is a homomorphism to the base field, I claim that chi is a star character. That is, it preserves the involution. To prove this result, we first take an arbitrary self-adjoint element of our algebra. So we know that the spectrum is real. This implies that the spectrum of its image, and here we calculate the spectrum with respect to the complex numbers, is also real. Well, indeed, we know that a unital homomorphism between unital algebras doesn't increase the spectrum. Here we don't assume that A is unital, but we know that the unitization of a sister algebra is also a sister algebra. So we can extend chi to the unitization of A, and the result will be a unital character of the unitization. And it doesn't increase the spectrum. So since the spectrum of A is real, it follows that the spectrum of chi of A is also real. But this means precisely that chi of A is a real number. So we see that chi takes self-adjoint elements to real numbers. Okay, and if we now take an arbitrary element in our algebra, we can decompose it in the following way: B plus IC, where B and C are self-adjoint elements. This is very easy, and this was discussed at the previous lecture. If we now calculate chi of A star, so what is A star? A star is B minus IC. So this is chi of B minus I chi of C. But B and C are self-adjoint. And we have just proved that in this case, chi of B and chi of C are real numbers. And so chi of B minus I chi of C is exactly the complex conjugate to chi of B plus I chi of C, just because they are real. And this is nothing but chi of A complex conjugate. And that's it. So we have shown that chi preserves the involution. So it's a star character. Another useful corollary of the previous result, that is, I mean, of the fact that the spectrum of a self-adjoint element is real, is the following spectral invariance result, corollary 2. Suppose that A is a unital C-star algebra, and suppose that B is a closed star subalgebra of A, such that the identity of A belongs to B. So they have the same identity. I claim that B is spectrally invariant. B is spectrally invariant in A. So let's recall this means that the spectrum of any element of the smaller algebra calculated with respect to the smaller algebra is equal to the spectrum calculated with respect to the bigger algebra. So in the general case, the spectrum calculated with respect to B can be bigger, but in this case, they are the same. Or equivalently, this means that we have the following equality, which means that each element of B, which is invertible in A, is also invertible in B. Okay, so let's prove this result. So suppose that little b is an element of B, and that this element is invertible in A. So we have to show that B inverse, the inverse element, sits in the same subalgebra B. So we do the following. We look at B star B and observe that this element is now self-adjoint and is still invertible in A. So B is invertible. This implies that B star is also invertible. So their product is invertible. But now this element is self-adjoint, and we know that its spectrum is real. The spectrum of this element, calculated with respect to the smaller algebra B, is real. So for each non-zero real number t, the element B star B plus I t1 is invertible in B. Okay, so we take the inverse of this element. So what can we say about this element? What can we say about the behavior of this element when t goes to 0? Well, it's clear that this element goes to B star B inverse, because the inversion in our algebra A is continuous, and all the elements B star B and this element are invertible in A. But this element, the inverse of this element, sits in B, and B is a closed subalgebra. So this implies that B star B inverse is also in B. And we have the following identity. So B star B inverse, B star B is 1. But now we know that this element sits in B. Okay, so what can you say about little b? We can say now that little b is left invertible in the smaller algebra B. Little b is left invertible in B. Okay, now we can now apply similar argument to the element BB star. So now we apply similar argument to the element BB star. And we see that now that B is right invertible in B. But of course, if we have an element which is left invertible and right invertible, this element is invertible. It's a simple exercise. And this is exactly what we wanted to prove. So a closed star subalgebra of a C-star algebra is always spectrally invariant. This is very useful. Okay, now we are almost ready to prove the Gelfand-Linework theorem. Before we can do it, let's recall a standard result from general topology. Namely, we will need the Stonewire Strass theorem. We will need this theorem in the following form. Suppose that X is a locally compact Hausdorff topological space. And suppose that A is a star subalgebra in C0 of X. And we suppose that A satisfies the following condition. First, we suppose that A separates the points of X. And second, we assume that for each point in our space, there is a function f in the subalgebra which doesn't vanish at X. So the theorem states that in this case, A is dense in C0 of X. So this is the Stonewire-Strass theorem. Traditionally, this result proved for compact Hausdorff spaces. And if X is compact, we usually assume that A contains the function which is identically 1. In the locally compact case, of course, we cannot assume this because A is, sorry. So in the locally compact case, the function that is identically 1, of course, is not in C0 of X. So condition 2 here is a replacement of this. So we require that for each point, there is a function which doesn't vanish at X. It's a simple exercise to show that the compact version of this theorem implies the locally compact version. This is very easy. Okay. Okay, now we are ready to prove the Gelfand-Linework theorem. Suppose that A is a commutative C-star algebra. Then the Gelfand transform of A, which acts from A to C0 on the maximal spectrum, is an isometric star isomorphism. Okay, so first of all, let's show that the Gelfand transform is a star homomorphism. So we take an arbitrary element in our algebra and an arbitrary point in the maximal spectrum, which is identified with the character space of A. And we apply gamma to A star, and then evaluate this at X. So by the definition of the Gelfand transform, this is just X evaluated at A star. But we already know that X is a star character. So this is the complex conjugate of X of A. That is the complex conjugate of gamma of A evaluated at X. And so this means that gamma is a star homomorphism. Okay, so gamma is a star homomorphism, and this implies that its image is a star subalgebra in C0 on the maximal spectrum. So it's a star subalgebra, And it's easy to see that this subalgebra satisfies the conditions of the Stonewire-Strass theorem. Well, why is it so? First of all, it's a star subalgebra. Next, it separates the points. By the very definition, you have two different characters. Then, since they are different, the evaluations of these characters on some elements from the algebra are different. And this means exactly that the image of the Griffin transform separates the points. And we have also to check this condition too. So for each element in our space, there is a function which doesn't vanish at x. But this is also trivial because we consider only non-zero characters. So this condition is satisfied. And now the Stonewire-Strass theorem implies that gamma of A is dense in C0 on the maximal spectrum. Okay, now to complete the proof, we have to show that gamma is isometric. First of all, we'll show that gamma is isometric on self-adjoint elements. Well, indeed, if little a is a self-adjoint element, then, well, we know that always the norm of gamma of A is equal to the spectral radius of A. This holds for all elements in any commutative Banach algebra. But since A is self-adjoint, the spectral radius equals the norm. And we see that gamma is isometric on self-adjoint elements. And now finally, if we take an arbitrary element in our algebra, we do the same trick that we have used at the previous lecture when we proved that all star homomorphisms to C star algebras are continuous. Namely, we apply the same to A star A. So by the C star axiom, gamma of A squared, the norm of gamma of A squared is equal to norm of gamma of A star gamma of A, which is the same as the norm of gamma applied to A star A. But A star A is self-adjoint, and we already know that for self-adjoint elements, gamma is isometric. So this is the norm of A star A. And finally, we apply the C star identity again, and we see that this is the norm of A squared. So we see that gamma is isometric, and since its image is dense, and the image of an isometry is always closed, we conclude that gamma is an isometric star isomorphism. Okay, so this completes the proof. Let's now discuss a useful category theoretic interpretation of this result. First, let's recall the following category theoretic definition. Suppose that we have two categories, A and B. And suppose that we have a covariant functor. A covariant functor f from A to B. From A to B. Then we say that f is an equivalence between A and B. If there is another functor, there is a covariant functor G, which acts in the opposite direction from B to A, such that G composed with F is isomorphic, is naturally isomorphic to the identity functor on A, and F composed with G is naturally isomorphic to the identity functor of the category B. The functor G is sometimes called a quasi-inverse. The quasi-inverse of F. And this functor is unique up to a natural isomorphism. So any two quasi-inverses are naturally isomorphic. Okay, now we introduce introduce some notation. We denote by say C U C star the category of commutative unital C star algebras. So the objects of this category are commutative unital C star algebras. And morphisms are unital star morphisms, which are, by the way, automatically continuous. Now we have the following proposition, which is immediate from our earlier results. So we have two categories. The dual of the category of compact topological spaces, compact Hausdorff topological spaces, and the category CU C star, commutative unital C star algebras. Here we have two functors. The first functor is denoted by C. It acts from the dual of the category of compact spaces to the category of commutative C star algebras, and it takes each space X to the algebra of continuous functions on the space. And we have a functor which acts in the opposite direction. This is the functor max, which takes each commutative unital C star algebra to its maximal spectrum. So now I claim that these functors are equivalences of categories. And moreover, they are quasi-inverse to each other. Namely, if we compose C and max, this functor is isomorphic to the identity functor of CU C star by means of the Gelfand transform. And if we compose them in the opposite order, then the resulting functor is naturally isomorphic to the identity functor on the category of compact spaces by means of the natural isomorphism epsilon, which was already discussed in the previous lecture, and which sends each point of a compact space X to the respective evaluation character. So this is the category theoretic interpretation of the Gelfand-Naimark theorem in the unital case. In the non-unital case, it's also possible to give a similar result, but it is slightly more delicate. So probably we'll discuss it a bit later after we discuss multiplier algebras. Well, anyway, morally, this result states that all essential information about a compact Hausdorff topological space is contained in the algebra C of X. So this result is a classical example of a complete duality between algebra and geometry. By the way, another result of the same kind is a categorical form of Hilbert's Nullstellensatz, which states that the category of commutative unital finitely generated algebras without nilpotence is dual to the category of affine algebraic varieties over the complex numbers. Results of this kind lead directly to non-commutative geometry. If we speak about the C-star algebra part of this theory, then the fundamental principle of this part of non-commutative geometry is that an arbitrary unital C-star algebra can be considered as the algebra of continuous functions on a non-compact, on a non-commutative compact topological space. That is, on the space which doesn't actually exist. So this may seem paradoxical, but in fact, this point of view leads to a very deep and beautiful theory. And it turns out that many purely topological constructions, after we translate them into the dual language, make sense for arbitrary, that is not necessarily commutative C-star algebras. And the perfect example of such extension is K-theory. So it turns out that topological K-theory of compact spaces is completely embedded into the K-theory of C-star algebras. Okay, now before we proceed, let's introduce some useful notation. Suppose that A is a C-star algebra, and S is an arbitrary subset of A. Then we denote by C-star of S, C-star A of S, the intersection of all C-star subalgebras A containing S. And we call this set the C-star subalgebra of A generated by S. So it's clear from the construction that this is the smallest C-star subalgebra of A, which contains S. In some cases, it is possible to describe this subalgebra explicitly. First of all, let's observe that in a general case, if S is an arbitrary subset, then this subalgebra equals the closure of the linear span of all finite products A1 to AN, where each element AI sits either in S or in S star. And N is an arbitrary natural number. So this is the explicit description of this subalgebra. This is more or less easy because the right-hand side is easily seen to be a C-star subalgebra. And clearly, this is the smallest C-star subalgebra which contains S. We will need also a special case where A is unital. Suppose that A is unital. And little a is a normal element of our algebra. Then the C-star subalgebra of A generated by little a and the identity. This is the smallest unital C-star subalgebra which contains A, is the closure of polynomials into variables applied to A and A star. So here P runs over the polynomial algebra into variables. And of course, we must also take the closure here. This is immediate from previous observation, because in this case, each such finite product reduces to a monomial in A and in A star. And even more special case. So suppose that A is oh, sorry, I forgot to write explicitly that A is normal. So little a is a normal element. So it commutes with A star. And if little a is self-adjoint, if little a is self-adjoint, then the respective subalgebra generated by little a and the identity is the closure of polynomials in one variable applied to A. Okay, now let's now prove a useful application of the Gelfand-Narmak duality to star homomorphisms. So we'll prove the following rigidity result for star homomorphisms between C-star algebras. So suppose that A and B are C-star algebras, and phi is an injective star homomorphism from A to B. I claim that phi is isometric. So each injective star homomorphism between C-star algebras is, in fact, isometric. This is quite unexpected from the point of view of general functional analysis, because of course we know that there are many operators between Banach spaces, and even there are many homomorphisms between Banach algebras, which are injective, but which are not topologically injective, and of course which are not isometric. But for C-star algebras, this is impossible. So in some sense, the category of C-star algebras is rigid. That is, all injective star homomorphisms are isometric. By the way, this easily implies that each star homomorphism has a closed image. To prove this result, first of all, we may assume from the very beginning that A, B, and phi are unital. A and B are unital, and that phi is also unital, that is, it takes the identity of A to the identity of B. Because if this is not the case, then we simply take the unitizations of our algebras. To prove that phi is isometric, it suffices to show that phi is isometric on self-adjoint elements. If we show that if phi is isometric on self-adjoint elements, then we can apply exactly the same argument as in the proof of the Gelfand-Narmak theorem. Let's come back to the proof. If phi is isometric on self-adjoint elements, then exactly the same argument as here shows that phi is isometric. See the proof of the Gelfand-Narmak theorem. So take a self-adjoint element in our algebra, and let A1 be the C-star subalgebra of A generated by little a and the identity, and let B1 denote the C-star subalgebra of B generated by phi of A and the identity. We now have to show that phi restricted to A1 is isometric. We want to show that phi restricted to A1 takes A1 to B1 is isometric. And now we apply the Gelfand-Linework duality. So A1 and B1 are commutative unital sister algebras. So they are isometrically isomorphic to the algebras of continuous functions on compact Hausdorff topological spaces X and Y, where X and Y are the maximal spectra of A1 and B1 respectively. And because of the Gelfand-Linework duality, each such homomorphism is induced by a continuous map from Y to X. So phi is induced by continuous map F from Y to X. Let's now recall that phi is injective. Phi is injective. This easily implies that F is surjective. Because otherwise, we can take a function which vanishes on the image of F, and this function will be in the kernel of phi. So phi is injective, so this is impossible, and we see that F is surjective. And now we calculate the norm of phi away. Norm of phi away is, well, since phi is induced by F, this is just the norm of A composed with F. So this is the supremum over Y, A of F of Y. But F is surjective, so when little y runs over Y, F of Y runs over the whole space X. So this is the supremum over X of A of X. And this is just the norm of A. And that's it. So we have shown that phi is isometric. We have shown that phi is isometric on self-adjoint elements, but this already implies that phi is isometric. Okay. Now our next goal is to discuss the continuous functional calculus in C-star algebras. Okay, so suppose that we have a unital Banach star algebra. A is a unital Banach star algebra. Little a is a normal element of A. So roughly, what we are going to do is to give a precise meaning to the expression f of A, where f is a continuous function defined on a suitable compact subset K of the complex plane. So this will be our goal. Well, of course, we know that if f is a polynomial, then f of A is already defined. And you probably know that you probably know what f of A is in the case where f is the exponential function. In this case, f of A is given by convergent power series. So our goal will be to extend this construction to give a meaning to this expression for more general continuous functions, which are not necessarily given by power series. Okay, so this is our informal goal. let's now give formal definitions. We suppose that K is a compact subset of the complex plane, and we denote by little t the inclusion map of our compact set into the complex map, or into the complex plane. By definition, a continuous functional calculus for A on K is a continuous star homomorphism gamma A from the algebra of continuous functions on K to our algebra A, the continuous unital star homomorphism from C of K to A, such that this homomorphism takes a little t to our element A. So this is formal definition. I'd like to stress that the word continuous here, I mean the continuous functional calculus, it is called continuous not because it is continuous as a map, but because it is defined on the algebra of continuous functions. So for example, if we replace here in this definition the algebra of continuous functions by the algebra of holomorphic functions on some subset of the complex plane, then we speak about the holomorphic functional calculus. So the word continuous refers to the fact that this homomorphism is defined on the algebra of continuous functions. Okay. First of all, let's prove the uniqueness. We have the following result. If gamma A exists, then it is unique. Well, this is a simple application of the Stonewire-Strass theorem. Indeed, the Stonewire-Strass theorem readily implies that the subalgebra of C of K generated by the function that is identically 1, by the function t, and by the function t bar, is dense in C of K. Because it's a unital star subalgebra which separates the points. And that's it, because we know that gamma takes t to A, but gamma is a star homomorphism, so it takes t bar to A star, and so it is uniquely determined by the assumption that gamma of t equals A. Okay, now how about the existence of the functional calculus? We have the following simple necessary condition. If gamma exists, then the spectrum of A is contained in K. Well, the proof is also very easy because we know that each unital homomorphism doesn't increase the spectrum. So sigma of A, so A is gamma of T. And this should be contained in the spectrum of T when we consider T as a function, as an element of the algebra C of K. But this is exactly K. So little e is just the inclusion of k into the complex plane. This is the coordinate function on k. Okay. In the general case, I don't claim that this condition is sufficient. Here's a simple but useful exercise. Construct a unital Banach star algebra A and a normal element E such that the continuous functional calculus never exists. That is, there is no compact subset of the complex plane for which gamma A exists. Fortunately for C-star algebras, the above necessary condition, I mean this inclusion, is also sufficient for the existence of a functional calculus. So we have the following theorem. Suppose that A is a unital C-star algebra and little a is a normal element. Then, for each compact subset of the complex plane, K, such that K contains the spectrum, there is a unique continuous functional calculus for A and K. And moreover, if K is exactly the spectrum, if K equals the spectrum, then gamma is an isometric star isomorphism onto the C-star subalgebra generated by A and the identity. Okay, let's now prove this result. First of all, we may assume from the very beginning that K is exactly the spectrum. Well, indeed, if we already know that the functional calculus on the spectrum exists, and if K is a compact set which contains the spectrum, we can simply compose this gamma with the restriction map from C of K to the algebra of continuous functions on the spectrum. So this is the restriction map. And the composition will be the functional calculus on K. So it suffices to prove the theorem in the case where K is exactly the spectrum. Okay. So let's denote by B the C-star subalgebra of A generated by a little a and the identity element. So the B is a commutative C-star algebra. And let's also recall the spectral invariance result, which says that the spectrum of A calculated with respect to B is the same as the spectrum of A calculated with respect to the bigger algebra A. This is the spectral invariance. Let's now consider a map phi from the maximal spectrum of B to the spectrum of A, which is given by the following formula. So this is just the co-restriction of the Gelfand transform of A. We know that the range of the Gelfand transform is precisely the spectrum of A. This is one of the properties of the Gelfand transform. So phi is a surjective map onto the spectrum. By the properties of A hat, phi is surjective. I claim that phi is also injective. That is, if we have two characters, 2 points in the maximal spectrum of B, x1 and x2, and if phi of x1 equals phi of x2, so this means that A hat, this means that x1 of A equals x2 of A. But since x1 and x2 are star characters, so we know that now that we remember that all characters of a C-star algebra are star characters. So this implies that they are the same on A star. But B, let's recall the definition of B. B is generated by little a and the identity. So this implies that x1 actually equals x2. And so our map phi is injective. And so it is bijective. And finally, since the maximal spectrum of B and the spectrum of A are compact sets, compact spaces, we conclude that phi is a homomorphism. Phi is a homomorphism by compactness.
Did we check the continuity?
It's continuous because it's just the Gelfand transform. We know that the functional little a hat is continuous. So phi is essentially a hat, so it is continuous. And this is a bijection onto the spectrum. So by compactness, it is a homomorphism. By the way, this is the point where two different notions of the spectrum coincide. So the maximal spectrum of B is homomorphic to the spectrum of the element A, which generates the subalgebra B. Okay, so to complete the proof, to construct the functional calculus, we now draw the following picture. So this is the algebra of continuous functions on the spectrum. And we have an isometric star isomorphism from this algebra to the algebra of continuous functions on the maximal spectrum of B. Namely, this is the isomorphism phi dot. This is an isometric star isomorphism. And now we have the Gelfand transform. So B is a commutative unit of C-star algebra. So the Gelfand transform of B is an isometric star isomorphism. So we have here the inverse of the Gelfand transform of B. And B is contained in A. So we now define the morphism gamma that we are looking for as the composition of these maps. So by construction, gamma is an isometric star isomorphism onto B. And to complete the proof, it remains to show that gamma is indeed a functional calculus. That is, it takes a little t to A. So we have to check this equality. And why is it so? So little gamma is the Gelfand transform, the inverse of the Gelfand transform composed with phi dot. So we have to check this equality. We now apply gamma to both sides. So we have to check that phi dot of t equals a hat. But phi dot of t, by the very definition of phi dot, is t composed with phi. But this is precisely our definition of phi. So phi is, where's phi? Phi is given by the same formula as a hat. So phi is just the co-restriction of a hat to the spectrum. And this means exactly that t composed with phi is a hat. So okay, this is true. So gamma takes t to A. And so gamma is indeed a continuous functional calculus for A on the spectrum. And we have already proved that it is a isometric star isomorphism onto the C-star subalgebra B generated by little a and the identity. Okay. Let's now introduce some notation. First of all, let's observe that if f is a polynomial in one variable, then after we apply gamma to f, or more exactly to f restricted to k, what we get is exactly f of a. So gamma takes t to A, and since it's a homomorphism, it takes each polynomial in T, each polynomial f to f of A. And more generally, if f is a polynomial in two variables, say x and y, so let's define the function f tilde on the complex plane by the following rule. F tilde of z is f applied to z and z bar, the complex conjugate. Then again, it's immediate from the definition of the continuous functional calculus that gamma applied to f tilde restricted to k is nothing but f applied to a and a star. So essentially for the same reason, this gamma takes little t to a, but it's a star homomorphism. And so it takes each polynomial and in t and t bar to the respective polynomial in a and a star. So we can also denote this by f tilde applied to a. So this observation leads naturally to the following notation. So now from now on, for each continuous function f on the spectrum of A, we write f of A instead of gamma A of f. This is natural because of the previous observation, because it is compatible with evaluating polynomials on A. Okay, let's now prove some important but simple properties of the functional calculus. Our first result is the spectral mapping theorem. I claim that for each continuous function. So as before, we assume that A is a well, let's write it down explicitly. So suppose that A is a unit of C star algebra. It's a unit of C star algebra. Little a is a normal element. I claim that for each continuous function f on the spectrum of A, we have the following formula. The spectrum of f of A equals the image of the spectrum under F. So we already know that this short and elegant formula holds for polynomials. This is a pure algebraic result. And now we want to show that the same formula holds for continuous functions on the spectrum. The proof is a simple corollary of our previous result. Namely, what is sigma of f of A? Calculated in the algebra A. This is the spectrum of gamma of F. Now we use the spectral invariance again, and we replace here A, the algebra A, by this smaller subalgebra B, which was introduced in the proof of our previous theorem. So B is the C star subalgebra generated by little a and the identity element. Okay, but we already know that gamma is an isometric star isomorphism of the algebra of continuous functions on the spectrum onto the subalgebra B. And because this is an isomorphism, this is equal to the spectrum of F considered as the element of the algebra of continuous functions. But the spectrum of a continuous functions, the spectrum of the element of the algebra of continuous functions is precisely the range of this function. So this F of sigma of A. And that's it. Okay, another simple but useful property of the functional calculus is the so-called superposition property. The superposition property of the functional calculus is the following statement. So suppose we have a continuous function f on the spectrum of A and a continuous function g on the spectrum of f of A. Well, we can take f and apply it to g of A. Oh, sorry, just the other way around. We can take g and apply it to f of A. This is well defined because f of A is a normal element and g is a continuous function on the spectrum of this element. I claim that this is exactly the superposition of g and f applied to A. By the way, the right-hand side here is also well defined because of the spectral mapping theorem. So the range of f on the spectrum is precisely the spectrum of f of A. So the composition is well defined. Okay, to prove this result, let's consider the following homomorphism. Let's denote it simply by little gamma. It is defined on the algebra of continuous functions on the spectrum of f of A. It takes it to A by the following formula. Gamma of g is GF applied to A. And it's immediate that gamma is a star homomorphism. Gamma is a unital star homomorphism. And it takes little t, the inclusion map into the complex plane, to, well, t composed with f applied to A. Well, this is just f of A. You can now look at the definition of the continuous functional calculus, and if we recall that functional calculus is unique, we conclude that gamma is nothing but the functional calculus of the element f of A. And this is equivalent to this formula. So this completes the proof. Well, okay, so a little problem with the functional calculus is that in general it is not given by an explicit formula. And the reason is just the construction of this calculus. The construction of the functional calculus involves the inversion of the Gelfand transform, which is quite unexplicit. So we know that the Gelfand transform is invertible, but we don't have any explicit formula for gamma inverse. And this is the reason why the functional calculus is not given by an explicit formula. But there are some special cases in which such a formula exists. Let's now look at a couple of examples. Example, exercise 1. Suppose that A, the C-star algebra A, is the algebra of continuous functions on the compact Hausdorff topological space. So little a is an element of our algebra, which is always normal because the algebra is commutative, and f is a continuous function on the spectrum of A. And then I claim that the functional calculus is given by the following simple formula. So f of A is just the composition of f and A. And one more example, which is closely related to operator theory. Suppose that we have a measure space, X mu, well, let's assume that it is sigma finite measure space. Let phi be an essentially bounded measurable function on X. And let m phi denote the respective multiplication operator, which acts on the L2 space on X view. And this is just the pointwise multiplication. So it takes each function psi to the pointwise product phi psi. So I claim, and this is an exercise, that for each continuous function f on the spectrum of this operator, by the way, the spectrum of this operator is the essential range of the function phi, we have the following formula. The functional calculus is given by the following rule. So this is just, again, the multiplication operator by the function f composed with phi. By the way, when you do this exercise, you have to give a precise meaning to this composition, to this function, because in general, the essential range of phi is not the same as the range of phi. So when we compose such functions, we must be careful. Okay, so in conclusion, just a final remark. Sometimes it is, so far when we spoke about functional calculus, we considered only unital sister algebras. Sometimes it is useful to extend this construction to non-unital sister algebras. So let's briefly discuss the non-unital case. So suppose A is a sister algebra, not necessarily unital, and little a is a normal element of A. So we know that A is contained in the unitization of A, and that the unitization of A is also a sister algebra. And we know that for unital sister algebras, we have the continuous functional calculus. So if we now take a continuous function f on the spectrum, or more exactly on the non-unital spectrum of A, and the non-unital spectrum of A is just the spectrum with respect to the unitization of A, we can look at the element f of A, which sits in general case, it sits in the unitization of A. For example, if f is identically 1, then f applied to A is the identity of A plus, which is not in A. But, well, let it be a simple but useful exercise. By the way, let me also recall that 0 is always in the non-unital spectrum. This will be essential. So the exercise is to show that the element f of A sits in the same algebra A, even only if f vanishes at 0. So if we apply the functional calculus to such functions which vanish at 0, the result, f of A, will be the same algebra A. And in this case, we have a well-defined functional calculus in A. So this will be a homomorphism from the ideal in the algebra of continuous functions, which consists of those functions that vanish at 0, to the algebra A. So here's the picture. This is the functional calculus in the unitization. And if we restrict it to the respective maximal ideal, say I0, then we get a well-defined homomorphism from I0 to A. Okay, so that's all for today. And at the next lecture, we apply the functional calculus to the study of positive elements in sister algebras. So by using positive elements, we introduce an order relation, a useful order relation on each sister algebra. And then we begin to discuss approximate identities, which is a very useful tool when working with non-unital sister algebras. Thank you.